Okay, on to section 4.2, the determinant of a square matrix. So where we stand is we have defined the determinant of a 2 by 2 matrix. We've defined the determinant of a 3 by 3 matrix, and that determinant of the 3 by 3 in terms of several determinants of 2 by 2s. The determinant of a 3 by 3 matrix is defined in terms of 3 determinants of 2 by 2 matrices. That's a pattern. So to section 4.2, plan here is to define the determinant of an n by n matrix. Determinants are only defined for square matrices. We'll do so recursively. That is, we'll define the determinant of an n by n matrix in terms of n minus 1 by n minus 1 submatrices of A. And we've seen this before because we defined the determinant of a 3 by 3 in terms of 3 determinants of 2 by 2 matrices. That means this is potentially computationally monstrous. So we'll have some techniques to simplify the computations. First, a minor matrix, capital A sub ij of an n by n matrix, capital A, is the n minus 1 by n minus 1 matrix obtained from A by eliminating the ith row in the jth column. And notice the capital A comes with a couple of subscripts, capital A sub ij. So there's a total of n squared minor matrices for a given n by n matrix. We don't need all n squared of them, fortunately. Let's look at an example. Here's a 3 by 3 matrix, A, with the usual notation for the entries. And we want to find the minor matrices A11, A12, and A13. So, to the supplemental notes. Okay, capital A11, that would be the matrix, the submatrix of matrix A that we get by eliminating the first row and the first column, ith row, jth column. So first row, first column. Okay, so that'll just leave us with these little entries down here. So capital A sub 11 will be the matrix with entries A22, A23, A32, A33. Notice there's no ones. And we've seen this kind of pattern before in the definition of the determinant of a 3 by 3 matrix. For capital A sub 1, 2, the minor matrix, will eliminate the first row and the second column, I and j, ith row, jth column. And that'll leave us with 4 entries, A21, A23, A31, A33. I can't quite say no ones or twos, but I can say we've eliminated the first row, so there's no first subscripts of 1, and we've eliminated the second column, so there's no second subscripts of 2. So that's the pattern. When we look at A13, we'll simply eliminate first row, third column, leaving us with this little minor matrix with these entries here, same pattern on the indices. Back to the notes. Okay, we're going to use those minor matrices to recursively define the determinant of an n by n matrix. So what we'll do is first we're going to define a thing called a cofactor. Lots of definitions, eh? The determinant of minor matrix capital A sub ij times -1 to the I plus j is called the cofactor of the entry lowercase a sub ij in the matrix, the original matrix, and it's denoted lowercase a sub ij prime. Okay, so we're taking determinants of the minor matrices, which are good to go if they're size 2 by 2 or 3 by 3. And then we're multiplying those by a power of -1. Well, power of -1 is either +1 or -1. It depends on whether the exponent, the I plus j, is even or odd. So let's find some cofactors. As an example, number 12. Here's a 3 by 3 matrix. Find the cofactor of entry 3. Okay, entry 3, it's in the second row, first column. So this is the lowercase a sub 1, a sub 2, 1, second row, first column. This is the entry lowercase a sub 2, 1 of matrix A. And we want to find the cofactor of that. That would be a power of -1 times the determinant of the associated minor matrix, to get used to the vocabulary. The minor matrix is determined by eliminating the row and column that contain this entry. Eliminate the row and column, and that'll leave us with the minor matrix, capital A sub 2, 1, with entries -1, 2, and 2, 1, -1, 2, and 2, 1. But in addition to that, there's the power of -1, and that exponent on -1 is the sum of the indices over here on the lowercase a. So we're looking at the cofactor lowercase a sub 2, 1 prime. So we'll take the 2 and the 1, add them together. That becomes an exponent of -1. And this thing here is what we just defined as the cofactor of an entry in matrix A. Okay, so A sub 2, 1 prime would be -1 cubed, just -1. It'll be plus or minus 1. In fact, we've seen some alternating and plus minus signs in our previous experience. It's this power of -1 that's going to explain that. So we get negative determinant of capital A sub 2, 1, 1. That would be negative determinant of this minor matrix. Taking determinants of 2 by 2 matrices is a piece of cake. So we'll get -1 times 1 minus 2 times 2 as given here. Of course, there's a negative sign out front, leaving us with -1 minus 2 is -5 with a negative out front, leaves us with a cofactor of 5. Which really has no meaning to us. Determinants have no particular meaning to us just yet. Trust me, determinants are useful parameters, and they tell us things about matrices. Later on, we'll use them to compute eigenvalues and eigenvectors, and those are totally useful. Back to the notes. Okay, so there's an example of a cofactor and an observation, a suggestive observation, as further motivation as to how we're going to define determinants of n by n matrices. We had determinant of a 3 by 3 matrix, and lo and behold, it can be expressed in terms of cofactors. The way we had dealt with this was we took the A11 entry and multiplied by the determinant of this little minor matrix down here. That little minor matrix now carries with it the title, capital A sub 1, 1, the notational title, capital A sub 1, 1. And remember here, around a matrix, the little absolute value looking bars actually indicate determinants. So we've got A11 times the determinant of this associated minor matrix. In the computation of determinants of 3 by 3 matrices, we then subtracted A12 times the associated minor matrix we get by eliminating the row and column containing A12. That'd leave these two entries and these two entries. Well, that's the minor matrix capital A sub 1, 2. So we'll subtract off this entry times the determinant of the associated minor matrix. Switch back to positives. That was our definition for 3 by 3, but you see where that alternating plus minus stuff is going to come from with those powers of -1 when we deal with this more generally. And finally, we took A13 times the determinant of the associated minor matrix in our current lingo, which would produce this as an expression for the determinant of a 3 by 3 matrix. That's the same thing we had before. It's just written in terms of determinants of minor matrices here, in terms of just elements like we originally did it. Oh, but we can take the determinants of these minor matrices and replace those, plus or minus, with cofactors. A11 prime, this cofactor would be -1 to the 1 plus 1, -1 to the 2, just be 1, times the determinant of this minor matrix. So we can replace the determinant of A11 with the cofactor A11 prime. And we're going somewhere with this. We've got that goal in mind instead of just swamping you with letters. How about A12 prime? Well, that was -1 to the 1 plus 2. -1 cubed is negative determinant of this associated minor matrix. So we're going to take this negative sign. This is why we had that -1 to powers. We're going to take that negative sign. It becomes part of the cofactor. And the rest of the cofactor is the determinant of the associated minor matrix. So the -1 determinant capital A sub 1, 2, that is the cofactor lowercase a sub 1, 2 prime. Down here, we're back to positives. 3 plus 1 is 4. -1 to the 4th, just 1, +1, times the determinant of that minor matrix. So when we first defined the determinant of a 3 by 3 matrix, it was just A sub ij's flying all over the place. This means the same thing, at least it's a more concise notation. And this is called writing the determinant in terms of cofactors. It's called a cofactor expansion of the determinant of matrix A. Now we've gone along the first row in all these computations. We'll liberate ourselves from that here shortly. But contained in this is all those A sub ij's and all those little determinants of 2 by 2s. It's a pile of arithmetic that's contained in these symbols. There's a pile of arithmetic contained in computing determinants. All right, so we're about to give a recursive definition for the determinant of an n by n matrix. If you want to find, for example, the determinant of a 4 by 4 matrix, in order to do so, you're going to have to compute 4 determinants of 3 by 3 matrices, which in turn, each of those is computed by taking 3 determinants of 2 by 2 matrices. Told you so. Here's a determinant right upstairs of a 3 by 3 matrix, and it involves these 3 determinants of minor matrices. Those minor matrices are 2 by 2. They came from eliminating a row and a column of this 3 by 3 matrix. So, same idea, iterated. Our definition will be given in terms of cofactors. Okay, so big definition, big difficult definition. We'll decipher it with applications, but the formal definition is, we'll define the determinant of a 1 by 1 matrix as its single entry. If you like, we can define the determinant of a 2 by 2 matrix the way we were doing it, with going down the diagonal and then subtracting off the back diagonal. It's called determinant of a 3 by 3 we've been through. So we've actually done determinants of n by n matrices for n equals 1, 2, and 3. This is done more generally by setting it up for n equals 1 and then basing anything bigger on that recursively on those smaller values of n. So for n greater than 1, suppose the determinants of order less than n have been defined, and they have for n equals 1, 2, and 3, at least so far. Take a matrix A, capital A with entries lowercase a sub ij, let it be an n by n matrix. Define the cofactor of a sub ij the same way we did above. A sub ij prime is -1 to the I plus j power times the determinant of capital A sub ij, where capital A sub ij is an n minus 1 by n minus 1 matrix obtained from the original matrix A by eliminating the ith row in the jth column of matrix A, like we did before. Then define the determinant of matrix A as the determinant of A is A11, A11 prime, plus A12, A12 prime, up to A sub 1n times A sub 1n prime For fans of sigma notation, that's a sum from I equals 1 to n of a sub 1I times a sub 1I prime. All right, so what we're doing is staying with this first index as 1. So that means we're staying in the first row, and we're letting I range from 1 to n. So what we're doing is running along the first row in this particular definition. We're taking matrix entries and multiplying them by cofactors. You see these here cofactors with primes? That's got powers of -1 in it, in such a way that the coefficients involved in the cofactors will run plus, minus, plus, minus, plus, minus, plus, minus. You've seen the pattern. Geez, we've only done it for n equals 3, but it went plus, minus, plus. So there'll be this alternating of signs because of those powers of -1 in them cofactors. All right, let's make sense out of that. And it looks straightforward, and where's the problem? Well, the problem is in these cofactors. That's a bunch of determinants of smaller things, is what it amounts to. So they've buried a world of sins here in terms of how much arithmetic must be done. And it's buried in them cofactors. All right, let's find the determinant of this 4x4 matrix. Okay, so what we'll do according to the definition is we'll take this entry, eliminate the row, the column, consider the minor matrix. Ouch, it's 3x3. This may take a while. We'll find the determinant of that 3x3 matrix. We'll move over to this entry, consider the determinant of the associated minor matrix by eliminating first row, second column, and there'll be a power of -1 in there as well, and so forth. So we'll have to take 4 determinants of 3x3 matrices. 4x4 matrix is going to give us 4 determinants of 3x3 submatrices. And each of those 3x3 submatrices have determinants calculated using 3 2x2 matrices. Well, let's do it. Okay, to the notes. Find the determinant. Okay. Good news is we only need 4 cofactors. This thing got a total of 16 cofactors, 1 for every entry. We only need 4 of them. Gee, we're going along that first row. There's a 0 in that first row, so that's got to be some kind of good news. Okay, definition says when n equals 4, the determinant of this matrix will be A11, A11 prime, A12, A12 prime, and so forth. Okay, I know the entries A11, A12, A13, A14. They are just the first row of this matrix, though they are respectively 2, 1, 0, 1. So we'll pick up a 2 here, a 1 here, a 0 here. I don't have to worry about that. We've got 0 times something. I don't care what the something is. The product's still 0. And then A14 here, which is 1. So we'll have 2 A11 prime from this 2, 1 A12 prime from this 1, entry A sub 1, 2 in the matrix, 0, that third term is gone. How convenient. A14 prime with a coefficient of 1. So plugging in the entries in the matrices. Now we got to find these cofactors. So we need, I'll take it back, we only need 3 determinants of 3x3 matrices. Well, thanks A13 entry, which was 0. That saved us from finding one of those cofactors. You know, if we had more zeros, we could save a whole bunch more time. Of course, that'll be a strategy on down the road. Okay, so let's see. A11 prime, we'll take the 1, 1 entry of matrix A, eliminate the row and column containing that entry, leaving us with this little 3x3 minor matrix. Here it is. We'll take the determinant of that minor matrix and multiply it by power of -1. That power of -1 is the sum of the indices over here. 1 plus 1 is 2. -1 squared is +1. All we need is the determinant of that minor matrix. It's a 3x3 matrix. We got that covered. Following our definition, I am intrigued by the presence of these zeros here. They'll be helpful in what we'll do. We can make better use of them, but I'm following what we know at this stage, which is definition of determinant of a 3 by 3 matrix says take 2 times the associated minor matrix, though we didn't talk like that when we introduced determinants of 3 by 3 matrices. Minor matrix was defined in this section. Then we'll subtract 1 times the determinant of the associated minor matrix here. Then we'll add 2 times the determinant of this little minor matrix. Do the arithmetic. I won't bore you with the details. And we end up with a cofactor A11 prime of, when all the dust settles, -14. Looks like the zeros, they played a useful role. They simplified the arithmetic. Anyhow, A11 prime is -14. Okay, let's do A12 prime. Okay, so for that, we'll have A12 prime is -1 to the 1 plus 2. So it'll switch over to a negative out here. And then we'll take the determinant of the associated minor matrix. Okay, associated minor matrix. Let's glance back at that. A12. So we'll eliminate the first row in the second column. That'll leave us with a minor matrix with entries 3, 1, 2, first row. 4, 1, 4, 1, 2, 1 for the other two rows. 3, 1, 2, 4, 1, 4, 1, 2, 1. We get that -1 to the 1 plus 2 out front. -1 cubed. Switched over to a negative now. Determinant of the minor matrix. It's a 3 by 3 matrix. I'll follow my definition. Not any zeros at all involved in these computations. Anyhow, the determinant of that 3 by 3 matrix is, I think it's -7. We had a negative out front. That'll create a +7 ultimately. Keeping eyes on negative signs and all that stuff. So we get the second cofactor, A12 prime, is 7. Third cofactor, third important cofactor, is A14. We didn't need to worry about this cofactor because of the matrix entry of 0. But for A14, we'll go to the 1,4 entry, eliminate the row and column. We'll be looking at this matrix, 3, 2, 1, 4, 0, 1, 1, 0, 2. Should be what we have here. That's what we have here. We've got -1 to the 1 plus 4 is 5. Is that 2 consecutive negatives? It was supposed to change sign, plus minus, plus minus. Well, it did. We just didn't look at the A13 prime. So sure enough, these powers of -1 have gone positive, negative, positive for A13 prime, but we didn't have to compute it, so we skipped it to negative. So we do have that alternating positive, negative thing that was predicted by these powers of -1. We need to take a determinant of this 3 by 3 matrix, throw a negative in front of it, and so we'll get, following through the computations, we get 14 apparently. Okay, so now we've got all 3 relevant cofactors. We knew the determinant could be written as entries times cofactors. Okay, we use the 2, 1, 0, 1 entries to produce 2, 1, 0, the missing A13 prime cofactor, plus 1 times A sub 1, 4, as above. We computed each of these numbers, so plug in the values we had from above for those cofactors, and the determinant's -7, which has absolutely no meaning to us. Is it obviously right or wrong? I don't know. I can't interpret it as anything in particular. So I don't know what to make of the value -7, but there you go. There's the computation of a determinant of a 4 by 4 matrix. And this is where I'd say you like this. Well, not at this stage because it doesn't mean anything to you. And if we showed all our work, that was a bunch of arithmetic. So actually sitting down and doing this by hand is quite time consuming. So maybe we can do something about that. All right. One thing we can do to take advantage of the presence of zeros is the following. So if you've got zeros, and let's say lots of zeros in one particular row or column, then the following is useful. In this matrix we just did, gee, I got a couple of zeros here. If I could have used those two zeros, I would have been better off than going along this first row where I only had 1 0. So we're going to take expansions by minors of determinants along any row or column. Okay, theorem 4.2. I guess the proof of this is somewhere in the appendix. It's probably not for the faint of heart. It's based on mathematical induction, which is explained in an appendix as well. Anyhow, the statement is, we'll take it as given. Let A be an n by n matrix. Then if we take any r between 1 and n, and any s between 1 and n, we have that the determinant of A can be computed like this or like this. All right. Now they've chosen parameter r because what they're saying is, whereas before we went along the first row, we took A11, A12 through A sub 1 sub A sub 1n, along with the corresponding cofactors. They're saying you could go along any row. Take A sub R1, we're going along row R. R is between 1 and n. Times cofactor A sub 1R prime. Plus A sub R2, cofactor A sub R2 prime, up through A sub Rn, cofactor A sub Rn prime. So instead of going across the first row, it's the same pattern, except we're going across the rth row. So up here, for example, we could have expanded along this third row instead of expanding along the first row. And in the second one, they're fixing the second index as S between 1 and n. Second index tells you which column you're talking about. So what they're saying here is, if we'll go to the S column of this matrix, then we can take matrix entries times cofactors, matrix entries times cofactors, and so forth. So we can compute the determinant the way we defined it in terms of the first row. We can compute the determinant by expanding along any row, or we can compute the determinant by expanding along any column. Back to that previous example, who's your favorite column? Well, this guy with 2 zeros in it. So we could have used that theorem to expand along this second column instead of the first row. Then we'd need 1 times a cofactor, which would be a first determinant of a 3 by 3 minor matrix with some negative 1s thrown in, plus 2 times the determinant of a second 3 by 3 minor matrix. But from there on out, it's zeros. So we would have to have calculated the determinants of 2 3 by 3 matrices instead of 3 3 by 3 matrices. Here's a bad idea. Suppose we extend it along the third column. No, I'm sorry, the fourth column. No zeros. Oh, we'd had to compute 4 determinants of 3 by 3 matrices. So this allows you, if they're present, to take advantage of zeros. Here's your problem. There ain't zeros there. None of this really matters. It's the same amount of arithmetic. If we only had a way to introduce zeros, but we're talking determinants here. Sure, we can do some row reduction stuff, but maybe that has an effect on determinants, or maybe not. And we'll have a way to know how determinants are affected by row operations, and that'll allow us to introduce zeros, do some bookkeeping, keeping track with how determinants change, and then take advantage of this. For now, this just tells you you could expand along any row or column according to that same pattern. Now, I'll guarantee you these cofactors, they're going to go positive, negative, in terms of the powers of -1. Or I guess they could start negative and go negative, positive, negative, positive. It depends on the even and oddness of the sum of those indices. If r plus 1 is even, we'll have -1 to the even times some determinant stuff. If r plus 1 is odd, we'll have -1 to the odd. So it'll be positive or negative. I can't tell you unless I know more about r and 1. Is r plus 1 even or odd? That determines whether these start with positives or negatives. But they absolutely, we get that alternating positive, negative produced by those powers of -1. And there's some other numbers floating around as well. But those coefficients are definitely alternating positive, negative. Okay, to put a name on it, we had taken an expansion of the determinant by minors on the ith row of A, and we used the subscripts involving the r's here. This, we've taken an expansion along the sth column, the expansion of determinant of A by minors on the sth column. So with that in mind, let's take a determinant of this matrix. See lots of zeros, loads of zeros in the first row. Nothing wrong with the first row. Loads of zeros in the first column. For variety, let's use the first column. Also, geez, and that 15 and 57, the arithmetic could be ugly, but if we think ahead, maybe we can work our way around that, depending on how we expand. All right, I say, let's use theorem 4.2, and let's expand along, I choose the first column. You want to choose the first row, you go right ahead, there's nothing wrong with that. But when I do this expansion, if we're along the first column, we're going to have 0 times something, plus 0 times something, plus 0 times something, plus 1 times, positive or negative, I forget, we'll have to figure that out, times the determinant of a minor matrix. And it'll be this little 3 by 3 minor matrix up here. Hey, we won't have to deal with the 15 or the 57 by expanding along column 1. If we expand along row 1, we won't have to deal with the 57. We'll have 0 plus 0 plus 0 plus 1 times the determinant of this minor matrix. So the 15 will still play a role. The 57, it looks like, ultimately doesn't play any role in the computation of the determinant, given the other numbers. Anyhow, I want to expand along the first column for the sake of illustration. So we'll have, let's see, we'll have -1 to the 1 plus 1. First column, we're using the A11 entry. So we'll have positive 0, I want to say. When we move to the 1, 2 entry, we'll have -1 cubed. We'll have a -0 times the determinant of an associated minor matrix. I don't care what that determinant is because we're multiplying by 0. And I'm not terribly constrained to do the plus minus thing, but I'm trying to get you thinking, oh yeah, it goes positive, negative, positive, negative. So that's why I've introduced the negative signs there, even where they're not needed, to catch the pattern. So anyhow, A11, A21, A31, A41. Okay, so let's see, we'll have a -1 to the 4 plus 1. That'd be -1. Yeah, that's right, there's a negative there. The matrix entry is 1, and the associated minor matrix is 0, 0, 1, 1, 2, 0, 4, 5, 9. Let me make it big. Okay, so we need to compute the determinant of this 3 by 3 matrix. All right, well, we can use our definition. Actually, let's use our definition, which was an expansion along the first row. Well, good idea, because it's got 2 zeros in it. But, geez, if it looked a little different, we could expand that determinant of a 3 by 3 along different rows or different columns as well. And you do so to take advantage of locations of zeros. Hey, there are more zeros in the first row than anywhere else, so we'll do it along the first row. So we've lost this stuff here. Don't lose the negative sign that's out front. Take the determinant of this. We'll have 0, -0, plus 1 times the determinant of this little minor matrix. 1, 2, 4, 5. We've got other minor matrices here. Nobody cares because they're being multiplied by 0. That's the advantage of having the zeros. Determinant here, 1 times 5 minus 2 times 4. Do the arithmetic. It looks like we get a value of 3 out, and the determinant of that matrix is 3. So this took way less computations than the previous one. Yeah, well, duh, it's because of all the zeros. So the zeros saved us a bunch of work. I'm probably going to skip a lot of the proofs in this. They're fairly lengthy. They're based on math induction. You'll look at mathematical induction when you take math reasoning, our 3000 class, math 3000. But let's look at pictures at least on this and make this plausible. claim here is show that the determinant of an upper or lower triangular square matrix is the product of its diagonal elements. And we'll just illustrate it for upper triangular. Lower triangular would be similar. Upper triangular matrix was a matrix that had below the diagonal only zeros. Lower triangular had above the diagonal only zeros. So if I were to transpose this, we'd get a lower triangular matrix. Okay, so we're looking at taking a determinant of this kind of matrix, and the claim is the determinant is the product of the diagonal elements. This U11 times U22 times U33, blah, blah, blah. Well, how would you like to expand it? Well, along the first column, of course, because all but one of the entries is zero. For all I know, U11 could be zero as well, but definitely the other entries are zero. So let's expand along the first column. In so doing, we'll have U11 times -1 to the 1 plus 1, positive, starts out with a positive, determinant of the associated minor matrix. We would get by eliminating row 1 and column 1. All right, so we'll produce a minor matrix that consists of these things, and lo and behold, the minor matrix is also upper triangular. Okay, so we'll take that determinant along the first column. That'll give us U11 times the determinant of this associated minor matrix plus a bunch of zeros. Right, plus 0, plus 0, plus 0 times whatever appropriate cofactors. Anyhow, you get all zeros there. Now we need to take the determinant of this smaller matrix. Well, it's upper triangular too. Let's go along the first column there. We'll have U22 times the determinant of the associated minor matrix plus a bunch of zeros. So that'll produce something of that form. And continue doing that. Every time you expand along the first column, you pick up this entry, eliminate the row and column. Next time, this will be the entry in the upper left-hand corner. So what you'll end up doing is peeling off those diagonal entries, and in the end, you reach maybe the final 2 by 2 or 1 by 1, depending on your perspective. You'll end up with the product of those diagonal elements. So the determinant of an upper triangular matrix is simply the product of its diagonal elements. We'll use that a handful of times in our stuff. And it should be plausible when you think how you take determinants by expanding along any row or column you like. You've done that a different way? Yeah, we could have probably ran along the bottom row instead of the first column because it had a bunch of zeros in it too. It would have led us to the same place. Let's see what's next. Yeah, next we'll talk about some properties of determinants. So I'll tell you what, let's cut the video there. We'll pick up with properties of determinants and see if we can't find a way to get some zeros in there. I like having zeros when I'm computing determinants. And I know how to introduce zeros using elementary row operations, but that might change the determinant of a matrix for all I know. Punchline here is going to be sometimes it does, sometimes it doesn't, but it's more than worth your trouble to do row operations and introduce zeros. So I'll see you shortly.